Okay, let's just dive right into this explainer. Today, we're putting on our geological detective hats. We're going to uncover the massive, dynamic, completely hidden forces that are literally shaping our planet. We're pulling clues from a fantastic science lesson plan that breaks down the spectacular geological wonders and, yeah, the terrifying hazards of the Philippines. We're going to look at the map of the Earth and figure out exactly why it behaves the way it does. To kick things off, we've got to ask ourselves this crucial mystery-solving question. Why does the Philippines have so many earthquakes and volcanoes? I mean, sure, it sits right smack in the middle of the notorious Pacific Ring of Fire, but what does that actually mean for the landscape and the people living there? Well, to figure that out, we have to look deep, deep beneath the surface.
So, here's our game plan. We'll follow a four-part roadmap. First, we'll look at Philippine geological evidence. Second, mapping tectonic plate interactions. Third, types of plate boundaries. And finally, simulating Earth's moving plates. Let's get to it.
Starting with Part 1, Philippine geological evidence, where we'll be investigating clues on the map. Now, layering these three distinct pieces of map evidence is like putting a giant puzzle together. It reveals the exact edges of tectonic plates, like the Philippine Sea Plate. So we identify clusters of earthquakes, we locate volcano belts, like the Luzon Volcanic Arc, and we spot those deep ocean trenches and massive fault lines, like the Philippine Fault System. When you stack all those together, the spatial patterns just overlap beautifully. These events aren't random at all, right? They follow the trenches and faults, giving us a literal blueprint of the incredibly active interactions hiding right beneath our feet. Since we're acting as detectives here, we absolutely have to distinguish a weak observational claim from a strong scientific inference. We don't just guess, we connect patterns to real processes. For instance, a weak claim like, the boundary is dangerous everywhere, is just vague. It doesn't tell us why. But take a strong scientific inference. I notice earthquake clusters near the trench. This may indicate a subducting plate. See the difference? That is the core of scientific map reading. We take direct map evidence and we use it to infer the invisible tectonic processes causing it. Moving on to Part 2, mapping tectonic plate interactions. Let's construct our tectonic model. This hazard-benefit duality is just fascinating. Tectonic activity isn't only about disasters. It actually provides the long-term resources and landforms that sustain life. Look, it's really easy to just focus on the scary stuff, right? The tectonic hazards like strong ground shaking, massive volcanic eruptions, think Mount Pinatubo, and tsunamis. But look at the flip side. These exact same violent processes provide incredibly fertile soil for agriculture. They provide abundant geothermal energy, which actually powers a huge portion of the Philippines. It's crazy to think about, but the very forces that threaten life are the exact same ones that create the foundation for it. All right, Part 3, types of plate boundaries. It's time to classify our tectonic culprits. First up, we need to understand the players on the board. We classify them as major and minor tectonic plates. Now keep in mind, minor plates, like the Philippine Sea Plate, might be smaller, but they can still be incredibly active and, honestly, super dangerous. Size absolutely does not determine geological importance here. A physically small plate can cause massive, region-altering events, all depending on how it interacts with its neighbors. When you look at the massive major plates and the smaller minor plates shaping our global puzzle, you'll immediately spot giants like the Pacific and Eurasian plates. But right there, tucked in the minor list, is the Philippine Sea Plates. And because it's surrounded and constantly being squeezed by those larger giants, it is forced into non-stop, intense levels of seismic and volcanic activity. It's really caught in the middle. The crucial point here is that we can actually predict what will happen at a boundary. We do this by comparing its relative motion, crustal changes, resulting landforms, and typical hazards side by side. Think of this like a cheat sheet for tracking exactly what happens when plates meet. Do they crash together, pull apart, or just slide past one another? Once we figure out the motion, we can predict whether crust is going to be created or destroyed, what kind of mountains or ridges will form, and exactly what hazards a local community might face. Let's break down the three distinct subtypes of converging boundaries step by step, just so we don't get overwhelmed by all the variations of plates colliding. Basically, when plates converge, they crash into each other. Simple enough. In step 1, oceanic-oceanic convergence, one dense oceanic plate sinks, or subducts, under another. This creates a deep trench, like the massive Philippine Trench, and a chain of volcanic islands. Then in step 2, oceanic-continental. The heavier oceanic crust dives beneath the lighter continental crust. That gives us a trench and volcanoes right on the edge of a continent. And finally, step 3, continental-continental.
Here, both plates are just too light to sink. So what do? They smash together and crumple upward, folding into gigantic mountain ranges. That's literally how we got the Himalayas. On the flip side, if convergence is crashing, divergence is separating. Divergent boundaries create brand new crust as they pull apart, allowing magma to rise up into the gap and form new ocean floor. But at a transform boundary, the plates just slide side by side. Crust isn't created or destroyed here. Instead, they snag on each other, they build up immense, incredible stress until they finally just snap, triggering severe, powerful earthquakes. And that brings us to our final section, Part 4, Simulating Earth's Moving Plates. We're going to predict landforms and prepare for hazards. Which leads us to a highly vital question when we're assessing hazard forecasts and community preparedness. If plates move, then what? Seriously, what can we expect to happen to the crust, the landscape, and the communities built right on top of it? Well, by matching the boundary motion to the likely crustal result, we can make solid, scientific hazard forecasts. We know for sure that transform boundaries give us earthquakes. We know convergent boundaries give us trenches and volcanoes. And we know divergent boundaries give us ridges. The absolute key takeaway here is that scientists use this wealth of geological evidence to map out risk zones. This is so communities can prep their building codes and evacuation plans. They do not use this to predict exactly what day or time a disaster will strike. It's all about long-term preparedness, not short-term panic. To summarize this perfectly, the lesson notes explicitly state, plate boundary motion explains patterns of landforms and geological events, while maps and models provide evidence rather than exact predictions. Maps and models are just incredible tools. They don't give us exact dates, but they completely decode the massive, slow-moving forces shaping our planet. They tell us the why and the where of these geological events. So, I'll leave you with this final thought to really spark your curiosity. How will you use this knowledge of our dynamic Earth to make safer, more informed decisions for your community's future? The evidence is literally all around us, in the shapes of the mountains and the lines on the maps. Keep asking questions, keep looking for those geographical clues, and keep exploring.